So next we are going to consider the following theorem, 5.3.3, and it tells us that if we have a function f from a to b, then if there is a function g from b to a, with the property that if we compose g with f, we get back the identity relation on a, then f is 1 to 1. Also, so far I've been mentioning identity relation on a, identity relation on b. Note that the identity relation is in fact a function. So let me just put a little note over here. So the identity relation on a set A to A is a function, because by definition, the elements of the identity relation are all of the form x comma x. And so this here is a function, and in fact, we have IA evaluated at x is equal to x for every single x in A. And so when I say identity relation, that's the same as saying identity function. And so now let's look at the second statement. The second statement tells us that if g is a function from b to a, with the property that f compose g is equal to the identity function on the set B, then f is onto. Now, a statement that is not in the text but is a consequence of these two is the following. If now we have a function g from b to a, with the property that g compose f is equal to the identity on a, and f compose g is equal to the identity on b, then f is bijective. But now from 1 and 2, we get that automatically, because 1 tells us that if g compose f is the identity, f is 1 to 1. If f compose g is the identity on b, then f is onto. Consequently, f is both 1 to 1 and onto, so it is bijective. And so that statement is just, the third statement is just a consequence of the previous two. But this here is a very important statement for proving that a function is bijective, because it allows you to bypass having to show that it is both 1 to 1 and onto, but rather if you exhibit the existence of a function g from b to a that has these two properties, this theorem allows you to automatically conclude that f is bijective. So now let us return to the example that we did at the very start of today's lesson. Following that, we showed that if we took the composition of g with f, then that gave us the identity on the real numbers minus the set containing the element 3. And similarly, we showed that if we took the composition f compose g, then this was equal to the identity on the real numbers minus the set containing the element 1. So now the theorem 5.3.3 tells us that f is bijective. And so we get this here without having to go through showing that it is 1 to 1 and onto like we did in the previous lesson. We get the now as an automatic consequence of the theorem. But actually more is true. We also have, by the same result, that g is bijective. Because if now if we switch the ordering in the theorem and take our g to be f, we see that the same still holds. We have the function f, and then we take the composition, we have identity relations on their corresponding domains, and now the theorem tells us that g is also bijective. And so this result that we're about to prove is actually very important, and keep this in mind whenever you have to show that something is bijective. Sometimes, if you're working with an explicitly defined function like these here, it sometimes is convenient to just exhibit what the inverse function is and then conclude it is bijective by the theorem 5.3.3. So let's go ahead and prove the theorem. So let's start off with 5.3.3. So I'm going to do the scratch work for 1. So we want to show that f is 1 to 1. And so we want to show f is 1 to 1. From our last lesson, we know that it suffices to show that f of a equals f of b implies that a is equal to b. So let's go ahead and assume that we have f of a equals f of b. So how do we go from there to concluding that a is equal to b? Well, the assumptions give us the existence of a function g, such that if we compose g with f, we get back the identity on a. So what we are going to do is compose both of these values by g. So we're going to take g of those values. So now we have g of f of a. And since these are equal, and g is a function, that means that the input for f of a would be the same output. Will give us the same output. So we have g of f of a is equal to g of f of b. So both of these are equal. But now, this here, rewriting it like this, g compose f, this is the same by definition, g compose f evaluated at a, which is equal to g compose f evaluated at b. But g compose f is the identity on a. So now we have that this here is the same as the identity on a by assumption. And this is equal to the identity on a evaluated at b. But this is going to give us back, when we evaluate the identity function at a of x, this will always output x. And so in this example, the identity function on a outputs back a, and the identity evaluated at b just output b, and we get what we want. We have that now f is 1 to 1 since we have proven this portion right here. And so that takes care of the scratch work for the first statement. So let's go ahead and do the scratch work for the second statement. So now we want to prove that f is onto. So to prove that f is onto, we need to take an element in b and exhibit that there is a value in a that maps to it. So want to show f is onto, and so we want to have we want to choose a lowercase b in the set b, and so it suffices to show that there exists some a, lowercase a in the set a, such that f evaluated at a gives us back b. So that's what we want to do. Now, how do we go about this? Well, we have our element b in the set b, and we know that g maps from b to a as a function, so we're going to go ahead and take g of b. What is this? We don't know. But what we do know is that if we compose g of b with f, then we can apply the assumption that f compose g is equal to the identity on the set b. And so now that will give us, upon taking f of this, so I'm going to just go ahead over here, apply f, and so this will give us f of g of b, which by assumption is going to be f compose g evaluated at b. But now this is the identity function. F compose g is the identity on b. So by assumption, that's the identity on b evaluated at lowercase b, which gives us back lowercase b. And so we got that this here, upon applying f, gives us back b. But now this is telling us that g of b, if we take f of g of b, we get back b. So now we can take a, now let a equal g of b. Then f of a is equal to f of g of b, which is b. And that's what we wanted to show. We wanted to show the existence of some a such that f of a is equal to b, so we show it's onto. And of course the third statement now follows automatically, as I mentioned earlier, from the previous two. So let's go ahead now and formally prove this. For the formal write-up, we have f is a function from a to b, g is a function from b to a. And now we're going to do the first statement. We're going to suppose that g compose f is equal to the identity on a. And we're going to let x comma y be elements in a with the property that f of x equals f of y. Since we want to prove that f is 1 to 1, we want to show x is equal to y. So now we're going to proceed just exactly as we did with the scratch work. So observe that f of x equals f of y implies that g of f of x is equal to g of f of y. Now by definition, this is going to be g compose f evaluated at x, which is now g compose f evaluated at y. And so now, by definition, and so now we have that g compose f is the identity on a evaluated at x, and of course here as well. And so here, since g compose f is the identity on a, and now this tells us that x is equal to y. Hence, f is 1 to 1. Or we can just say injective as well. And so that takes care of the first statement. Now let us do the second statement. So suppose that f compose g is equal to the identity on b, and let b be in, actually let me switch this to y, and let y be in b. And now what we want to do is prove that f is onto. But from the scratch work, we know that we just have to take our element a to be g of y. And so now I'm going to switch to x's. So now let x is be equal to g of y. And now we get the following. Then we have that f evaluated at x is equal to f of g of y, which is equal to f compose g of y, which is equal to the identity on b by assumption, evaluated at y, which is equal to y, since f compose g is the identity on b. Consequently, f is onto. And we're done with this case. And now 3, we can just say this follows. Automatically, from 1 and 2, and so now we're done. And so that finishes the proof for theorem 533. But now keep this in mind in the future if you're trying to show a function is bijective. Theorem 5.33 part 3 gives you a recipe for showing that the function is bijective without having to show explicitly that it is 1 to 1 and onto, because now we have done it in this proof. So once we find the function g, which happens to be the inverse function as we saw with our motivating example. Once we find that function g that has this property, that allows us to conclude f is bijective, and so is g. So the next theorem is a combination of the previous 3 theorems we have covered, 531, 532, and 533. And what it tells us is that if we have a function f from a to b, then the following statements are equivalent. F is 1 to 1 and onto, that is, f is bijective, is equivalent to the inverse function, the inverse relation from b to a being a function. And lastly, that's also equivalent to the existence of a function g from b to a with the property that g compose f is the identity on a and f compose g is the identity on b. The proof is just automatic from the previous statements. So if we assume, So let's go ahead and do 1 implies 2. So here, so this statement is just the statement of theorem 531. We have a function from a to b. If f is 1 to 1 and onto, then f inverse from b to a is a function. So this is theorem 531. For the next statement, we're going to do 2 implies 3. So now we are assuming that f inverse from b to a is a function. But if that is a function, we have theorem 532 that tells us that if f inverse is a function from b to a, then f inverse compose f is equal to the identity, and f is compose f inverse is equal to the identity on b. So now this is theorem 5.3.2, where g takes the place of f inverse. Because if we let g be f inverse, we have f inverse compose f, identity on a, f compose f inverse is equal to the identity on b, which is the conclusion in 5.3.2. So we got that statement. And lastly, we have 3 implies 1. And now for this one, we are assuming that there is some function g from b to a with this property. But now, the previous theorem, 533, comes in and tells us that if we have both of these conditions, the function is bijective. So that's the third statement that I added here. And so now we get that f is bijective. And so now this is theorem 5.3.3. And we're done. We're done with this proof. So before we cover our last result for the day, let us revisit our motivating example, where we had f of x equals x plus 2 over x minus 3, and g of x, 3x plus 2 over x minus 1. How did we construct g? Well, we applied the techniques we have previously learned to find the inverse function for f, and that's how we got g. So we know that g of x is the inverse function to f. But now, from a theoretical standpoint, can we deduce that g is in fact the inverse function based only on the fact that g compose f is equal to the identity on the real numbers minus the set containing 3, and f compose g is equal to the identity on the real numbers minus the set containing 1? And the answer is yes. And that's the context of our next theorem, which tells us that if we have a function f from a to b and a function g from b to a, with the property that the composition of g with f is the identity on a, and the composition of f with g is the identity on b, then in fact g is equal to f inverse. So let's prove this. So we're assuming f and g to be functions with the property g compose f is equal to the identity on a, f compose g is equal to the identity on b. Now, by theorem 534, we have that this premise 3 is satisfied. That's what we have. We have a function f and g that has this property. So 534 tells us that f inverse from b to a is a function. Then by theorem 534, f inverse from b to a is a function. So we got this statement. And now we want to prove that g is equal to f inverse. Well, what we are going to do is the following clever trick. And so first off, I'm going to go ahead and just write g. This is going from b to a. And so g goes like this. But what if we decided to go back to a via the identity on a? Well, this is going to give us the identity on a compose g of x is going to be identity on a evaluated at g of x, but the identity just outputs that same input to the same output, so this is just going to be g of x. So if we do identity on a compose g, is just back to g of x. So we're going to make we're going to use this in the following way. So then, observe that we have G, which is equal to the identity on A composed with G. So now we're using this observation that we just made here. Now we're going to use theorem 532, which tells us that the identity on A is equal to F inverse compose F. And so we have F inverse compose F is the identity on A compose G. And so here we have by theorem 532. But now notice that F inverse compose F, then G, by associativity, is the same as F inverse compose parentheses F compose G. And this allows us to use the assumption that F compose G is the identity on B. And so now we have F inverse compose the identity on B. And now we're going to make the following observation, that if we had done B goes to B, and then this goes to A, where the first B to B is identity on B, and B to A is F inverse, then when we take the composition, we're going to be taking F inverse of identity on B, evaluated at some lowercase b of B. This is just going to give us back F inverse of B. So in other words, putting in this identity on B is going to make no difference. And so this here is just a quick sketch of the idea for why we have that F inverse compose the identity on B is F inverse. But there's nothing special, of course, about F inverse in this case. You could replace this F inverse with any function, and you can then show that any function composed the identity on B is going to be that function, so long as the function in question goes from B to A. And so with that, we have that F inverse compose the identity on B is equal to F inverse, since F inverse compose the identity on B is equal to F inverse. And so I leave it to you to fill in this detail and make it precise, but the idea here is what we have in the scratch work. And now that shows that G is equal to F inverse, which allows us to now finish the proof. And so we are done, since we have shown that G is equal to F inverse, and that finishes it off for today's lesson. And so for our next lesson, we are going to we're going to skip section 5.4, we're going to go to 5.5, which is a short section on inverse images, and then we are going to start section 8.1, which is our first coverage of infinite sets.